Hi guys, welcome back to another lecture. So today we will be learning about discriminant analysis. So context of this lecture is like we will be moving beyond simple prediction to effective classification through projection. So in classification, utilizing projection to transform data into decision-friendly spaces, dimensionality, reducing features to most informative components, and separability, preserving and maximizing the gap between different data classes. So this will be the context for today's lecture. So let's recap our previous lecture. So in our previous lecture, we learned about machine learning, that models get trained using features and labels for predictions on unseen data. Then we learned about linear regression. So it is a closed form solution where parameters depend on mean and variance. And then we learned about logistic regression, which where iteratively weight gets updated using gradient descent for classifications. So why we need to handle high dimensions? So curse of dimensionality. Sparse data makes modeling difficult. So as you move forward, like when you increase dimension, the sparse data gets to increased, and the sparse data makes the modeling difficult. Now visualization, as we can't visualize beyond 3D, so it's like difficult for us to visualize a higher dimension data. Other than this, the if if there is ND space, then always the decision boundary will have dimension of n minus one. So our goal will be to find the most discriminative subspace. Now we will learn about Fisher discriminant analysis. So let's know what's the motivation behind it. Why not principal component analysis? So PCA is unsupervised, focuses on variance which may not align with class labels. Yeah. Now, FDA is supervised, explicitly utilize class labels to find separating direction. As in FDA, what happened? We use class label to separate two classes. To separate two class labels, so it explicitly utilizes class label to find a separating direction where to separate. Now, noise reduction. High dimension data often contains redundancy that obscures boundaries. Yeah, so in high dimension data, there is so much overlap. But when you reduce its dimension, it's happened that there is a complete separation between the data. So that's only it's written there. Now take a projection of this is the original space, and when we take a projection of this in 2D, 2D to like in 1D, when we take the projection, you can see that easily there we can make a decision boundary between these two data points. So projecting uh, data makes helps sometimes to find a decision boundary. So we project d-dimension data onto a line defined by vector w. Yeah, so we project on a line defined by vector w as y equals to w transpose x. Now decision rule. A threshold-based classification in 1D converts complex ND boundaries into simple rules. Now, Fisher criteria have two things. Our primary objective is always to maximize the separation between two classes. So we always try to maximize the distance between the class mean, different classes mean. And our secondary constraint is to minimize the variation within class is scatter or spread. So what we want that our data within the class should be totally what we say we are are not scattered, they are totally at one place, not spread much. So that we want it we want our objective is to maximize the separation between different class mean and to minimize the variance. Now let's formalize this thing. So how we will be how will we show the within class scatter, like how we will show this term to minimize the variance or to maximize the separation. So this is the within class scatter matrix SW, where this xn belongs to some class C1. So we are finding SW, which is for a particular class, and this is SB is the between class scatter matrix, which is the difference between mean of two classes. Now we will find SW and SB, and then we will find SW and SB, and then we will add it here. Like we will then after doing this, we will put it here. This is W transpose SB upon W by W transpose SW by W. So what does this ratio tells us? Like we always want to maximize the separation between these two classes. So we want to increase our numerator, and we always want to minimize the scatter. So we want to decrease our denominator. So overall, we want to maximize. This. Means overall, we want to maximize this value because we want to maximize the numerator and want to minimize the denominator. Now maximizing ZW leads to generalized eigenvalue problem. So that was an eigenvalue problem. And since SBW is always in direction of M2 minus M1, the solution will be. So what happening here? After this, yeah. So after this, we we differentiate ZW, and we get some equation. And in that equation is like W transpose SWW into SBW equals to W transpose SBW SWW. So in which W transpose SWW is a scalar and W transpose SBW is also a scalar. So after which weight become proportional to SW inverse into M1 minus M2 or M2 minus M1. So this is like weight will be proportional to SW inverse M2 minus M1. So there are two cases, isotropic and general case. What is isotropic? Isotropic is like when your spread is equivalent in all classes. If covariance is in both direction, in X and in Y. So if covariance is identical across classes, identity matrix, the direction is simply the vector connecting the means. But when the solution rotates the mean difference vector, the account to internal spread of the data. So when it is not isotropic, then that difference, the direction is not simply the vector connecting the means. There will be little bit of rotation or change. Now, if we generalize it, let's generalize this to the multi-class because it was binary class. So what will happen in multi-class? How we'll find within class cluster for multi-class? So here, we will get SW by doing sum of individual classes scatters. So we will find SK for each classes and then we will sum it. And for between classes scattered, we will find mk minus this m is the overall mean of all data and mk is the mean of particular class. So and nk is the number of samples in that class. So we will find sv by doing this thing, and then our objective here will be to find trace of SW inverse SB. Now, why we are doing trace of SW inverse SB? Because we want to, yeah. So SB this is actually SB upon SW. This is actually SB upon SW. So as we have learned in our previous binary class separation, it was W transpose SB upon W upon SW transpose SW upon W. So in that case also we want to maximize it. So in this case also, like here there are multiple classes. So we have to add the variance, like this is the kind of we are adding the variance in all the directions and we want to maximize that. Yeah, so we want to maximize that. So in this case also SB upon SW, we want to maximize that value. So we are adding variance in all directions, and then we are for all classes because there are many more than two classes. So that's why we have to add for all directions, and then that is actually the trace. Now, what is the advantage of FDA? So this is like efficiency computationally simple, yeah, because we do matrix inversion, nothing. Correlation handles correlated features well, and small samples robust when even sample size is relatively small. Limitations is yeah, this assumes Gaussian class distribution. It also assumes equal covariance for all classes, and it also perform like for linearity, performance drops for highly nonlinear data. Now there is other two different types of discriminant analysis: quadratic discriminant analysis and regularized discriminant analysis. So this like one it solves one of the limitation, which is assumes equal covariance for all classes. So in quadratic discriminator, which allows its classes to have its own covariance matrix, result in a quadratic decision boundary. Here there will be not linear decision boundary. Here it can be quadratic decision boundaries. You can see here, as there are many different decisions boundary here you can see only linear. Yeah. Now regularized discriminant, a compromise between LDA and QDA using parameter alpha is RDA. So here we are taking both QDA and LDA, and we are combining it through alpha as a parameter. So this is regularized discriminant. Now, what is the practical implementation pipeline? First of all, we will pre-process a standardize and centering of features. Then we will do PCA optional. Like it's an optional task. You initial dimensionality. Firstly, what happened? People do initial dimensionality reduction through PCA to avoid singular matrices. I guess you know about singular matrices, and then they do FTA projections to find the optimal discriminative subspace, and then after that we apply our classifications rule. Now yeah, this is the pro tip: always use cross validation to tune the RDA parameter threshold selections for this alpha. Yeah, you have, I know everyone do cross validations for hyperparameter tuning. The summary is like maximize class separability by balancing between class distance and within class scatter. Yeah, that two goal, like the two objectives. And optimization solved as generalized eigenvalue problem involving SW inverse. I guess if you have done a course in computational method of optimization, you must be knowing how to solve that equation, what we have seen. So it was just a generalized eigenvalue problem in which we use Lagrange multiplier to solve that part and get W is directly proportional to SW inverse SB, or directly you can also do it by differentiating and equating it to 0, and then like you will be getting W is directly proportional to SW inverse M1 minus M2. Yeah, but you have to open SB, and when you will be opening SB, you will be seeing it as M1 minus M2 into M1 minus M2 transpose, and then M1 minus M2 transpose into W is also a scalar. So we will remove all this thing, and that as W, which is in other side of equal to, will come this side, and W will then be proportional to SW inverse SB. If you guys want me to explain this part more, please comment. I will be solving it in my copy, and I will show you or share on the video. So yeah, so FDA turns high dimensionality complexity into simple one-t-type decisions. If you have any question related to this topic, you can comment it down. I will surely address it in next video, or whenever I will see your comment, I will reply it. These are my sources. Thank you. You can also comment what else you want to learn from me. I will be surely making videos on it. Thank you.